Lesson 5.4, Scatter Plots and Regression. Now in this lesson we're going to talk about what we do when we have two sets of data, and this is called bivariate, the analysis of a relationship between two variables. And when we have two variables to compare, we usually make a scatter plot, which is a set of data graphed as ordered pairs on a coordinate plane. When we graph that data on a scatter plot, we then try and graph a line over it, which is called the line of best fit, a line that closely approximates the set of data. In other words, if you have tracks in the snow, you would make a sidewalk where those tracks are, and that sidewalk best approximates the tracks. And when you do that, when you put a line on it, you get a measure of correlation, which is a measurement of linear relationship. It measures the direction and strength of a linear relationship between two variables. And a correlation might get confused with slope because it does relate to positive and negative slope. So if it's growing as you go to the right, it goes up. It's positive, it goes down as you go to the right, it's negative. But that's the only connection it has with slope, because correlation must have a value between 1 and -1. It cannot be greater than that. So a correlation of 0 means no relationship. A correlation of 1 means perfect positive correlation, and -1 is a perfect negative correlation, and we'll talk about that later. When you have that situation, you start to talk about causation. If you see that there's a relationship, then you would naturally ask, does one variable cause another? And this is, in statistics, instead of saying dependent and independent variables, we call them response and explanatory. So the independent variable, the x, is now in statistics is called explanatory, and the y variable, or the dependent variable, is called the response, because you have many more real-world applications for in statistics for these variables. So instead of independent and dependent, we call them response and then explanatory. Regression, okay, is looking at that line of best fit and looking for linear relationships. Okay, so the study of how a response, or a dependent variable y, changes as an explanatory or independent variable x changes. Because we want to talk about, in real world situations, businesses want to know what causes what. Medicine, in the medical field, they want to know what causes what. So they look for these relationships so that they can manipulate them and use them to our advantage. So scatter plots, an example here, we have home runs and runs batted in. You have two variables, okay, and you're going to compare them. Notice that the home runs are the x-axis and runs batted in are the y-axis. So in this particular situation, we would call the x-axis the independent or the explanatory variable. Runs batted in would be the dependent or the response variable. Now if we graph them as a coordinate, so 33 and 114 as a coordinate, alright, we have 33 over, 114 up, and that's that point right there. And we would plot each point in that manner. And that would be a scatter plot. Here's an example that we have to create. A table below shows the number of women serving in the United States Congress during the years 1987 to 1999. Make a scatter plot that shows us. Now notice that we have a little quiver here, which means it's not that they're jumping all the way to 100. They're going from 0 to 100. We talked about this in misrepresenting data, but in this particular case there's no data before that, so we'll just go ahead and focus on this particular area of the graph. So that's okay. And that's, as a knowledgeable statistician, we notice that, but we know it's not misrepresenting our data. So again, we graph these as coordinates. Okay, now the x-axis is sessions of Congress, so that's why this is considered, the first column is x, and this is y. We look for the relationship, so we would plot 100 and then 25, which would be about here. This is just approximations here. 101 and 31, so 101 and 31, about here. 102 and 33, so a little bit bigger than the last one. 103 and 55, about there, and 104 and 58 about there, and then 105 and 62 about there. Now if we look at this line, or this collection of data points, it looks like it's going in a direction. Alright, the sessions of Congress, the 100th session, 102nd session, so as Congress progresses through all its sessions in years, the number of women in Congress are going up. Okay, so I'm going to jump ahead for a moment and say, well, if we were to approximate this line, then one would say it seems to be following this path. It's going up. Now, like I said with correlation coefficient or correlation number, it's between -1 and 1. Since this is going up to the right, we would say the correlation is positive. But at this point, we're not going to say anything more than that. Okay? Predicting equations, or now line of best fit. Line of best fits are predictor equations. Now, there's 3 different terms you can use for line of best fit. We say line of best fit generically because that means the line that fits our data best. It's also called regression line or least squares line. There's 3 different terms that we could use. And as mentioned already, when data is put onto a scatter plot, they may seem to form a line or a path on the graph. The correlation coefficient is used to measure how well the data lie in a straight line. So again, if you have a correlation of 0, the data does not look like it's on a straight line, and we'll look at that on the last slide. So line of best fit is the line that best seems to fit the data. The equation of the line of best fit is the regression line. So if you write your equation for that line, we'll talk about how to do that, it's called a regression line. But you can still call it line of best fit and so on. Alright, so how do you do that? Well, let's look at this. We have an example here that says according to a certain prediction equation, the cost of 200 square feet of storage space is $60. The cost of 325 square feet of storage space is $160. We have 2 coordinates here. So if we take that information and interpret it like we have at the beginning of the semester, and we would say that the first coordinate represents, and we're going to say that since cost depends upon square footage, let x represent the amount of storage. Okay, so one coordinate then would be 200 square feet, and then the dollars it costs to have that. Another coordinate would be 325 square feet, and the cost is $160 for that. So these are 2 coordinates. So now we're going to be asked to go back to our prior knowledge of making equations from 2 coordinates. If you recognize this, we have the slope formula, the difference in y's or the difference in x's. So they do the subtraction and they get this number here, which represents slope. Alright, now we want the equation. So if you remember again, we use point slope method, and that gives us this equation. We plug in our slope we found, which is 0.8. We plug in one of the 2 coordinates. They chose 60 or 200 and then 60 for x and y. That's this point they chose. And plug that in and solve for y, and you get your equation. And this represents your prediction line or line of best fit. And they call it a prediction line because you could plug in a square footage for x, and from that you'll find out what it will cost you, approximately. Okay, so use the table on the right to draw a scatter plot, write a prediction line, and then use the prediction line to predict the missing value, which is 10. Alright, so based on what we've done here then, let's plot our information. We have 1 and 1. So approximately there. We have 3 and 5, which is approximately there. 4 and 7, about there. 6 and 11, about there. 7 and 12, there. 8 and 15, about there. Now, again, I'm just going to approximate this line, but it looks like it goes like that. So we have a positive slope. Alright, but we're going to do it more specifically and go back to what we've been taught. And when you're doing a line of best fit, it's best to choose points on the end. Okay, so let's just choose 1 and 1, and we'll choose 8 and 15. We're going to follow the same method as before. Now again, this is 1, 1, and this is the coordinate 8, 15. So rise over run. So we're going to find the change in y's. So I'll go 15 minus 1. Change in x's, 8 minus 1. And we get 14 over 7, which is 2. That's the slope. Now we go to our point slope method. And we go y minus y1 equals our slope, in parentheses x minus x1. So y minus y1, and we can pick one. I want to pick this one because that looks like it has numbers that are easy to use. So I put a 1 in. The slope is 2, and x minus the x value, which is 1. So we have y minus 1 equals, I'm going to distribute this and get 2x minus 2, add 1 to both sides, and y equals 2x minus 1. Now this is our line of best fit, approximate line of best fit. We didn't do this the official way, which we'll need a calculator to do because it's quite a bit of calculation. But approximately this works. And from this approximation, we can find out what 10 will give us. So again, we would say y equals 2 times 10 minus 1. That is 20 minus 1. So y is 19. That predicted 19. So it gives you a value of x. You plug it in, and the line of best fit, or the prediction line, gives you a value of 19. So if we were to go out to 10, so this is 7, 8, 9, 10, way out here, it's approximating 19 up here somewhere, and that's pretty close. And that's what that's used for. So a little bit of review there for coming up with the equation of a line. Alright. I'm going to stop here, and this ends lesson 5.4, part A.